Chapter 7, what counts as a design problem? In the previous chapter, Chapter 6, we were talking about why the study of ethics is important to engineers. And part of that argument, or the argument was made there, was that simply looking at the ways in which a design could have ethical implications is enough to make engineers aware of the problems that can result from their design choices. So it's partially a conscience-raising sort of exercise. You might not have thought about ethics as part of an engineering practice. Now, once it's been pointed out to you that there are ethical implications at all stages of a design, at all stages of the creation of an artifact, now you can become more sensitive to things that might pose ethical problems as you go further in your engineering career. What Chapter 7 does is shows you examples of design problems. So very briefly, just want to go over some of those that are presented in Chapter 7 for you, just to point out some of the high points or the highlight some of the important aspects of design problems. So what counts as a design problem? What counts as a morally problematic design? So we're going to look at 3 example cases. The first case is the Cadillac trunk case. The Cadillac trunk case deals with a problem that resulted from forcing a Cadillac trunk to close all the way. Cadillac had created a trunk mechanism whereby the user would pull the trunk down most of the way, and then the remainder, the last 6 or 8 inches or so of closing the trunk, was done automatically. And it turns out that this design was problematic because of the damage that could be done if one tried to close the trunk all the way. Second example is an X-ray machine problem, and this was a problem that we could look at in a couple of different ways. One, it could be viewed as a programming error. The other would be a safety error, that there weren't mechanical mechanisms. So it could be a software issue. We could view this as a mechanical issue. And the third is the defibrillator. And this is an example of problems with a device that was to be implanted to regulate heartbeats. And there was a problem with the design of the wires that were used. So we're going to look at each of these cases and just point out some of the things that should have been considered in the design solution and the problems that this causes. So the lessons learned from the Cadillac case. The Cadillac case, as I mentioned, was one in which if the user pushed the trunk down, Cadillac had designed the trunk such that a hydraulic system took over and closed the trunk the rest of the way. Now, if you forced the trunk down, as you note from your reading, what would happen is the trunk would be damaged. Now, in one, we could possibly open some of this up to operator error. So maybe this isn't necessarily design error. The operator, had they read the manual, would know that all they have to do is push the trunk down a bit and then the hydraulics would take over. So avoiding the problem of damaging the trunk. But this sort of leaves out the consideration of a legacy issue. And a legacy issue, as you know from the text, is one in which there are certain assumptions made about how things work. So most of us know how a trunk works on a car. What most of us don't know is that certain cars would have this hydraulic system. So it would be very easy to make a mistake or not be aware of how a trunk works or how a new trunk works with this hydraulic system. So in part, when the engineer looks at the design, it should be said, well, how will the operator use this? Well, assuming the operator reads the manual, thinking that they need to read a manual for the trunk, or that the person selling the Cadillac is going to have to inform them that there are some things that they want to brush up on, because although most of us know how to close a trunk, you don't know how to close a trunk if you're a Cadillac owner, at least until you read the manual. So there is a legacy issue, and this should probably have come to light at the beginning of this design, that given that people, as the book gives an example, say the doorman at a hotel, and let's say that they're taking the luggage out for you and they go to close the trunk on your car. Can we assume that somebody who's closed trunks for years and years is going to know that this particular model of car has this special trunk? Now, it wouldn't be problematic if by closing it by hand, pushing it all the way down, didn't cause the mechanism to break. If that were the case, maybe there's no issue. Because they say, well, that's fine. It's not meant to be used that way, but it won't damage the trunk if it is. And also we want to note here that there's a harm that's caused by this particular design. Now, in part, there's one obvious harm, and that's the harm that if the trunk is broken, if someone pushes it down because either of operator error or because directly related to operator, this legacy issue, that it was just something that no one could be reasonably expected to think that there's a difference in a trunk lid, then the harm caused is the cost imposed on the owner to get the trunk fixed. Now, as the book notes, one of the things we want to know about harm, or what we should be thinking about in terms of harm, is that we really don't have to ask whether the harm is significant. So it doesn't have to be a lot of harm in order for it to be an engineering ethics problem. The very fact that I impose a cost on someone is a harm, and it's particularly morally relevant when I could have easily avoided that harm. So an alternate design could have been such that it doesn't allow someone to push it down, or there's a safety mechanism that stops the trunk from being damaged. So in this case, and what the textbook notes, is that we don't want to get sort of caught up on what is a harm. Philosophers debate this all the time, all different levels of harm, but as an engineer, if I can avoid a harm, even if it's a small harm, then why not avoid it? So this goes back to the previous chapter where we're talking about the aspirational nature of engineering. You should strive for a foolproof design. And in this case, it doesn't seem that it would take much to create a foolproof design, at least one in which damage isn't done, harm, even if it's a small amount of harm, is avoided. So this is one of the things, that sort of the lessons we learned from a Cadillac case, that we should think about how it's going to be used, how something that's been standardly used for, 70, 80 years now, how somebody who's been familiar with cars would use this, and whether we can avoid the harm in our design choice. So as I already mentioned, the nature of harm in this case, the test is whether there is a significant enough harm that could have been avoided, and the determination of harm is not limited to the loss of life, for instance, but extends to any setback and interest we have. So just to go back to the harm that I just mentioned, the test here isn't one where it has to be a life-threatening harm. It's just one, can I stop somebody from being harmed at all, from a setback and an interest? And clearly the interest is in me not buying a very expensive car and then having to get it repaired from something that one would naturally do. So we don't have to get hung up on the definition of harm. All we have to ask the question is there harm, and is it a necessary harm? All right, so those are really the two questions. Is there a harm, and is it necessary? And if we answer yes, there is a harm, and no, it's not necessary, then we should be doing something different in our design choice. Lessons of the X-ray machine. The interesting part about the X-ray machine example is that there's really no problem with the machine itself. The X-ray machine example is one in which the technician using the X-ray was separate from the area where the X-ray machine was actually doing its work. So a technician to be away from the radiation, to be out of the area, was in another room. And one of the things that the machine design didn't have was some sort of safety mechanism to make sure that there was no one on the X-ray table when it shut down. So the shutdown process was one in which the X-ray machine went down basically to the table, which in this horrible instance was one where it could crush a human being if they were on the X-ray table. So one of the things that we learned from the X-ray machine is engineers think how the design will work in situ. That is, how it will work when it's actually in practice. So you can have a wonderful design. You can have an automated design that shuts itself down, that powers down, that takes photos, takes the images, that transmits those images to another terminal. We can have a wonderful design, but then the question is, how is that design actually going to be worked in an everyday situation? It seems that in this case, the possibility for error was pretty great, because once you put this machine in practice where people are coming in and out of a room, where an X-ray machine may be taking several X-rays, so it might be a few minutes process where the technician may look away or be distracted for a moment, or possibly just simply waiting for a patient to be removed from the X-ray machine and taken back to their room, something that the technician may not be responsible for. So solving the problem of designing a good X-ray machine, is not the end of the design process. Part of that process is going to be how the machine will be used. Engineers need to think both technically as an engineer and creatively as to how the machine will be used. So let me plug a philosophy double major here. This is what we're attempting to do in both chapter 6 and 7, is to show you that creative thinking is also part of engineering. Looking at things from multiple perspectives, asking, sort of questioning how this will be used, where it'll be used, who will be using it, what happens when people use this, what happens to people who are in this sort of industry, how does the everyday workings of a hospital differ from the idealized situation of a hospital. All of these types of questions are the types of things one would ask if you were designing a machine to be used in a hospital setting. That is, how will it work in the conditions or under the conditions in which it will be used in everyday life? So engineers need to think about this. They need to think both technically about problem solving and creatively about the use and the context. Lessons learned. Defibrillator. So the defibrillator case was one in which the design of the contacts was not exactly conducive to being placed inside the body. Now, this seems like an obvious sort of design flaw. And so it really comes down to a very simple question. The thing we learned from this is, will the parts withstand implantation? So will the parts withstand implantation? Now, this seems something incredibly intuitive. If I'm designing something that's going to be placed inside the human body, then clearly I should be up on what types of conditions it will meet. So things like blood, the different chemicals in our blood or in our body. Liquid, can it withstand corrosion? How much acid is in the body? What happens when other chemicals are added to the body? So a person on various medications, if you have a heart condition, there's likelihood you're on medication. Does this change the content of the blood? So isolated from situations in which they will be used, these artifacts seem perfectly fine. Put into situations in which they will be used enough, will fail to work as they were designed to work to cause unnecessary harm, including death. So here's a case where we do have a life or death harm. By not thinking through the problem, by not saying, am I putting the correct parts in place? Am I using the right materials? Can this withstand sustained use over time? I'm actually causing harm and life-threatening harm and failing in my job as an engineer. If I'd engineered this device and didn't specify what type of parts ought to be used, then I am morally responsible for what happens.